the last class, the lab went long, and I couldn't get them out of the room, and they kept asking for more stuff and more stuff and more stuff. So they finally left, and I was able to clean up the lab. So unfortunately, we're getting started late today. And as we were talking earlier, what I've decided to do, since one student needs to take the final early, and I don't have the final made up for chapter 26 yet, and I don't have a lab for that one yet. I don't know if I could come up with one. So rather than continue in 26, I thought I'd go back to chapter 20, where I do have, I think, a test already made up, and I think I have a lab made up. I just don't have them run off or anything. But I think I have these. At least they'll be easier to reproduce than the other. So let's go back and chapter 20. Oh, yes.
Did you ever find the lab and test the lab for me?
Okay, I can look for it now, or I can do it at the end.
Can we do it now?
Pardon me?
Can we do it now?
Okay, I'm using class time, and we're already off to a late start. Can I give it to you at the end when we're doing lab or doing, have a good time to break?
I guess I had to take it Wednesday.
I'm sorry?
I said I probably had to take it Wednesday, and I had to take my mom somewhere at like 6.
Okay, well, it's 6 right now. What is it you need?
The test and the lab from Wednesday.
The test and the lab from Wednesday.
I think it's 16. From chapter 22.
You both got the electromagnetism labs and that test. There's the electromagnetic induction lab. Yeah. Okay. I've got to run it off, so I do have it. There, I think, is the test. Yeah. So I have to run that off. Okay, this is it. There's test 7. Do both of you need test 7?
Yes.
Okay. And the lab, I have to run off. Both of you need it?
Yeah.
Okay, let me go down and run it off. Man, no wonder this is. Okay. Let me pause this. All right, here's the problem. The end of, let's see. We have tomorrow morning our planning hearings is what they're called. And mine is from 10 to 11 tomorrow, which is unfortunate, and it's on the Birmingham campus. So that was meaning I was thinking I'd have to end my differential equation class early so I could get over there in time for the 10 o'clock meeting. However, one of my instructors did not send his material in, and I contacted him last Thursday, and he said he would get it to me Friday, which was really convenient because I was, had other plans for Friday, but I did get it and start doing, but he said he couldn't get me the documentation, which is also required, so he was going to bring that this week. So I've got to go over there first thing tomorrow morning to the Birmingham campus. I've already canceled my differential equations class because I got to get this material that he was late getting in. So, and put it together for the meeting that's coming up at 10 o'clock. And I have to stay for the beginning of the next meeting because we do some things with natural sciences, like I teach physics, so I'm going to meet with them for a half hour because I got to get back over here to teach my 12 o'clock class with a lab. So I'll be through at 3:30. So that's the next time I'm going to have any office hours. I didn't have any office hours last Thursday. I did have them, but I had to spend the whole time, if I wasn't advising students, I was putting together the student learning outcomes and unit plans, getting all the copies made and things that we needed, except for the stuff that he hadn't sent. So I put the rest of that together this weekend. I didn't have any time to do any grading whatsoever. So now I have this much grading to do. That's from last Thursday and today. So and I don't have any time in the morning. Now, if I could put my package together and have some time, I might get a few things graded before my hearing at 10. But then the earliest I'll be able to do anything else is tomorrow afternoon at 3:30. And hopefully I can get some stuff done then, but I know I have one student coming by on a research project, and that's going to take a while. And I think I've got other students coming by for registering and stuff. So I don't know when I'm going to have to be able to sit down and get that last test typed. Well, I've got it typed. I've just got to get it formatted as a test. So as soon as I get that done, I'll have that ready, knock on wood, on Wednesday. Okay, I sure hope I will anyway. So I'll try to get that done. Next, let me say this. This class, a really good class of, 8 students now? I believe so. And I have received one research paper in. Okay. I need them because I've got all this grading to do, mucho grading to do, and I don't want them all coming in during final exam week. So if you can get them in tomorrow, tomorrow or Wednesday, you still get 1 bonus point. If you turn it in Monday, no bonus points. If you turn it in Tuesday or later, you start losing points. Okay. I think I've returned to you your first test, haven't I? Okay. I can't return any labs because I still have one student who hasn't turned in any labs yet. So I've returned your first test, your second test, and your third test. And the fourth test, right? Okay. Okay. So as soon as I get the rest of the stuff in, I'll try to get those returned. Okay, now next Monday, I'll be returning everything. Labs, tests, except a research paper, because they periodically ask for samples of student writing. Like for this hearing we have, I had to put some samples of student writing in. So periodically we have to have that. So I can't return your research papers, but I can return your labs and your tests. Okay, so tonight we're going to start in chapter 20 and get as far as we can. Since we are starting here, I'm pretty sure we're not going to have time for a lab since we're already 45 minutes late getting started. So I'll get as far as I can in chapter 20, and we'll continue with that on Wednesday and hopefully get close enough to finish it so we can have our last lab on Monday, the the 31st. And that'll be the last day of class. And I just happened to note.
Is it for all your Monday?
I'm sorry?
I said, is it for all your Monday or Wednesday classes?
Yeah, all Monday or Wednesday classes, last day of class is Monday. Tuesday, Thursday classes, the last day of classes is Thursday.
So, are we going to have a third test in calculus?
I'm sorry?
Are we going to have a third test in calculus?
Yeah, that'll be the final exam. Yeah, and it won't be comprehensive. It'll be just the last chapter that we're working on. All right, I just realized I hadn't marked that. Okay, so any questions? Please get your papers in. And there's one other thing. I meant to say it in the last class too, and I forgot to. If you're 18 years of old or older and are a resident of Alabama, please, if you haven't registered to vote, please register to vote. The 31st, that's next Monday, is the last day to register before the primary for the Senate election, which is the 15th of August. So you have to be registered by Monday to vote on the 15th. For the city elections, do you live in Gadsden? Or do you live in Birmingham? Huh?
I go to Auburn though.
Okay, where do you vote?
In Lee County in Auburn.
Oh, okay.
Yeah.
Well, you can, if you need an absentee ballot, you need to get that. For the primaries, I would say pretty soon. And for the, and you're not voting in the Birmingham city. Do you live in Birmingham or somewhere else?
I did an absentee.
Where?
I think it did it. My grandma does, so she did.
Okay.
I did already.
Okay, but are you, what I'm saying is, where is your address? Birmingham?
It's Bessemer vote.
Oh, Bessemer. Okay, so you don't vote in the Birmingham elections either. So all y'all are interested in is that senatorial election. Please vote. My goodness, I can't think of a more important election we've had in a long time. So please vote on your absentee or whatever you do, but get it done so your vote will count. Okay. Sorry, I just need to get that political statement out there. Okay, we're doing chapter 20, or topic 20, induced voltages and inductance. Okay? Now, think back to our magnetism chapter. What are some of the connections we have between electricity and magnetism? Well, back in 1890, okay, if you think about that, that was 7 years after the War of 1812, okay? That was sort of that time of peace we had between the War of 1812 and the war between the states. So it was a fairly quiet time for us in the U.S. We were just sort of getting our feel for being a nation. And at that time, Hans Christian Ørsted, and I'm pretty sure he was from Netherlands. I'm not sure absolutely, but I believe it was Netherlands. Let's see if they say here. No, I don't see Ørsted done here. Okay? But anyway, Hans Christian Ørsted discovered an electric current does exert a force on a magnetic compass. So that was probably the first indication that there were connections between electricity and magnetism. The first evidence of a link between electricity and magnetism. Before that, they were completely separate. Magnetism was what you used for guiding ships, and electricity was what they used to shock your friends, okay? And maybe they were beginning to do batteries. Then, about 1831, okay, 12 years later, a British, I think both of them were British, Faraday and Henry, showed that a changing magnetic field could induce an electric current in a circuit. And we saw that in the magnetism lab, remember? A changing a magnetic field induced an electric current in a circuit. Remember when we turned the lights off and connect and disconnect, and the lights would flash on and say, that was a changing magnetic field creating an electric field. that led to Faraday's law, okay, which here is Michael Faraday. I don't know if you remember, there was an actor, Richard Chamberlain. To me, he looked so much like Richard Chamberlain. I don't know if you remember Richard Chamberlain. But this is Michael Faraday. He lived from about the time that our Constitution went into effect, around 1791. Actually, we were a little ahead of that, to 1867, which is after the war between the states. He was a great experimental scientist. I mean, he did a lot. He invented the electric motor, the electric generator, and electric transformers. Three of the big things we use in electricity today. He discovered electromagnetic induction, something that's crucially important today. In fact, that's used in generating electricity. And he discovers the laws of electrolysis. Quite a scientist. Brilliant. And very practical inventor. Okay? Michael Faraday. Now, here is Faraday's experiment, the one that he set up. And the thing is, here's the deal. What he did, he set up a battery here and wound it around an iron core. Okay? You see? Cores around there. He had it so it switched on and off. So either the battery was sending current through there or it wasn't. This was called the primary coil. This was an iron ring here, and here was a secondary coil. Now, there is no connection between these wires and those wires. No direct connection at all. You were creating a current in this circuit, but what was happening? You were measuring a current in this circuit that was not connected to a battery. Why was this happening? Because when you have a changing, well, first, when you connected this, the moving charges created a magnetic field. So this magnetic field magnetized the iron ring. That magnetized iron ring then made a current. But it only made a current not when it was fully magnetized, when the current was changing. So what was key here, when the switch in the primary circuit is closed, the ammeter in the secondary circuit at the right measures a momentary current and then it stops. We saw this in that lab. Were you there for the magnetism lab?
Yeah.
Okay. Remember when we changed when we did connect or disconnect, that's when we saw the current.
Yes.
When this was on full time, no current. When it was off, no current. It was only on connection and disconnection. That's what we showed in that lab. The EMF in the secondary current circuit is induced by the changing magnetic field through the coil in that circuit. So this is stuff we've already done in lab. So maybe, since we did it, we won't do a second lab on this. We'll see. Okay? So the primary coil is connected to the battery. Okay. So current can be produced by a changing magnetic field, first shown in this experiment by Michael Faraday. The primary coil is connected to a battery. Secondary coil is only connected to an ammeter. There is no current going through this coil from anywhere else, no battery or anything else. However, when the magnetic field was changing in the coil here, you got a current. When it was steady, you didn't get a current. When you connected or disconnected, that changed the magnetic field here, which created an electric current there. Only when it was changing. Okay? So, an induced EMF is produced in the secondary coil by the changing magnetic field. Now, if you choose Michael Faraday for your paper, there's a little blurb here. He's really a great, is often regarded as the greatest experimental scientist of the 1800s. That's really saying a lot. His many contributions, and you can read that. He obviously was a very good guy, too. I had not remembered this before, greatly influenced by religion, he refused to work on military poison gas for the British government. Good guy. Thank you very much. Okay. So that's Michael Faraday's experiment. No battery in the secondary circuit. We don't have this picture anymore. When the switch is closed, the ammeter reads a current, then returns to zero. When the switch is open, the ammeter reads a current in the opposite direction and then returns to zero. When there's a steady current in the primary circuit, ammeter reads zero. Okay? So what it says, it takes a changing magnetic field to induce an electric current. A changing magnetic field to induce an electric current. So this was Faraday's conclusion. An electrical current is produced by a changing magnetic field. I've said that several times now, it's pretty important. The secondary circuit acts as if a source of EMF were connected to it for a very short time. But of course there isn't one. It's going based solely on the changing magnetic field. It is customary to say that an induced EMF is produced when the secondary circuit, in the secondary circuit by the changing magnetic field created in the first circuit. That's your summary of Faraday's law. Okay? Now, section 20.1.1. Still 20.1 on the slide set, but now magnetic flux. Okay, an EMF is actually induced by a change in the quantity we call the magnetic flux. What do we mean by magnetic flux? It says, rather than simply a change in the magnetic field. It is a change in magnetic field, but it's a quantity we call magnetic flux. Magnetic flux is defined in a manner similar to electrical flux. Okay? Now, in case you've forgotten that, fields are vector quantities, fluxes are scalar quantities. So it makes them easier to work with. Magnetic flux is proportional to both the strength of the magnetic field passing through the plane of the loop of wire and to the area of the loop. So the magnetic flux is proportional to both the strength of the magnetic field passing through the plane of the loop of wire and the area of that loop. Okay? Here is the illustration of it, and this is in your text, bottom of page 657. You're given a loop of wire. That's all. Just a loop of wire. No battery, nothing else. Given a loop of wire. The wire is in a uniform magnetic field. Doesn't have to be cutting straight through it, just any angle there. Here's your uniform magnetic field going through that loop of wire. Okay? The loop has an area of A. The way they've done this loop is not very loopy, it's rectangular. Length by width. That would be your area of that loop of wire. If it was circular, you could do pi r squared. 2 pi r. Whatever in shape it is, it has some area. The flux is defined as, and the symbol for flux is this Greek letter phi, sometimes called phi, but not phi and phone. Okay, so this is pronounced phi. Phi sub b, that's magnetic. B stands for magnetic. Capital Phi sub b is your perpendicular component of your magnetic field. That's what B perpendicular means, times the area. Okay? So if this is going up, this magnetic field going like that, at an angle that is perpendicular, okay, angle to the area here, okay, and that's the angle between the field direction and the plane of the loop. If that angle is theta there, the area of this, okay, well, the flux is the perpendicular component of the magnetic field times the area, and the perpendicular component of that field is the field strength, B, times the cosine of the angle theta. Okay? B times cosine theta. Where cosine is greatest when you're perpendicular and least when you're parallel. Okay? So, cosine is greatest at 0. Okay, remember the area is a vector that points out this way. So when you're parallel to that, that's when the B is coming in the same direction as that, that's when you have the greatest flux. So it's the angle between, theta is the angle between B and the normal to the plane. That's supposed to be plane, not plan. Okay? I have found several little silly, whoops, let me get mine. Normal to the plane. And that's why we say the cosine of the angle, because the angle is the one normal to the plane. This is the plane here, that's the line normal to it, and the cosine would be the component of this flux in the direction of the normal to the area. The SI unit, System International Unit, for flux is the Weber, WB. Okay? Now there's another name. If you could write on Oersted, you could write on Faraday, you could write on flux, you could write on, and this Weber, capital B, capital W here. Why is the B included in the unit? Or wasn't it just W? I already used watts. W is the symbol for the unit for watts, named after James Watt. So that was already in place, so they had to use WB for Weber. What is a Weber? Well, let's take a look. It's a Tesla, that's the SI unit for field strength, times meter squared. So a Tesla meter squared, that's a Weber. So flux is the magnitude of the field strength in the direction, same direction of the normal to the area, okay, times the area, okay. Now, when the field is perpendicular to the plane, if this is the side view of that loop of wire, okay, the field is perpendicular to it. In other words, the area here is in that direction too, normal to that plane. Then the normal and the flux field strength, field area, are parallel to each other, so the theta is 0. Then you have the maximum flux, and that P sub B max would be the field strength times that area. Okay. If you put the coil in line with the field strength, so no field lines are being cut by that, you have 0 flux. Okay? When the field is perpendicular to the plane of the loop, as in A, then theta is 0, cosine theta is 1, and the phi, the flux, phi sub B, is phi sub B max, which is just the field strength times the area. When the field is parallel to the plane, in other words, the normal to that loop would be straight up. So now the angle is 90 degrees between the field and the normal to that loop. Then cosine of 90 is 0. You have absolutely no flux at all. Now, the flux can also be negative. Well, that's hard to picture here. But if the theta was 180 degrees, well, I have trouble picturing that because this is 0 degrees. What would 180 degrees be like that? You just turned it over. But if that indicated a series of coils and they were in the other direction, then that would make it obvious that would be 180 degrees. And therefore the flux could be negative. Now notice here, when you go back to this statement of flux, like we had before, this flux is a scalar quantity, no longer a vector. The field is a vector quantity, the area is a vector quantity, this is a dot product between the two, and therefore it's a scalar quantity, which does make it easier to work with. And that's why it can be negative. Okay? Now, finally on magnetic flux, the flux can be visualized with respect to magnetic field lines. The value of the magnetic flux is proportional to the total number of lines passing through the loop. That's why the area of the loop is important. The more lines that are passing through it, the greater the flux. If it's a real tiny loop, very few lines would be passing through it. When the area is perpendicular to the lines, the maximum number of lines pass through the area and the flux is at a maximum. When the area is parallel to the lines, no lines pass through the area and the flux is zero. So that's just another way of looking at it in terms of field lines. Okay? Now, there is a Applying Physics 20.1 Flux Compared that probably is a pretty good one to take a look at. And then there's Example 20.1, which is on magnetic flux. And again, pretty straightforward. I think you can do it. If you want me to see me work any of these, I'll be glad to. Okay? So, moving on to 20.2, which is Faraday's law of induction and Lenz's law. So here comes another name. Okay? Now this is the figure you see at the bottom of page 659. Okay? When a magnet is moved toward a loop of wire, the ammeter registers a current. Okay? Well, that makes sense, doesn't it? When you're moving this magnet toward the loop of wire, even though the loop is not connected to anything but an ammeter, there's no battery at all, but move this magnet toward there, at first very few field lines were being cut. When it's way back here, you move it in, you're increasing the number of field lines, and therefore you're getting a current. When the magnet is stationary, though, even though it may be very, very close to the coil, absolutely no current is being induced. But then if you move it away from it, you'll get the opposite current. If that was a negative coming in, it's going to be a positive going out. Okay? When a magnet moves toward a loop of wire, the ammeter shows the presence of a current. When the magnet is held stationary, even if it's very close, there's no current. And if the magnet moves away from the loop, the ammeter shows a current in the opposite direction. Let's see, if the loop is moved instead of the magnet, guess what? You still detect the current. It doesn't matter whether the magnet moves or the loop moves. All it takes is relative motion between the loop and the magnet. However you do it. You can move them both, move one, move the other. Either way, as long as there's relative motion between the two, you detect currents. Okay? Now, a current is set up in the circuit as long as there is a relative motion between the magnet and the loop. It doesn't matter which one's moving, just one of them has to be moving. The same experimental results are found whether the loop more moves or the magnet moves. Same results. The current is called an induced current because it's produced only by an induced EMF. There is no battery to produce an EMF. It's an induced EMF caused by the changing magnetic field. Okay? Or the changing magnetic flux, the way they like to call it. All right? The instantaneous EMF the instantaneous EMF induced in a circuit equals the negative time rate of change of magnetic flux through the circuit. The negative time rate of change of magnetic flux. Remember from the very beginning in physics, first thing we did was talk about distances or displacements. When you took the time rate of change, that gave you speeds or velocities. Took the time rate of change of velocity, you get acceleration. Get the time rate of change of momentum, you get force. Yeah, you're doing time rate of change all the time. Time rate of change of energy is power. Okay? Time rate of change all of it. So the instantaneous EMF is induced in a circuit equals the negative time rate of change of magnetic flux through the circuit. So in other words, the EMF is in the opposite direction of the rate of change of magnetic flux. If a circuit contains, let me go back for just a second here to this figure here. That's why, I don't know if you wondered about it or not, but that's why when you're moving this toward here, the flux is increasing. But look at what your current is. Negative. So that's when this is moving toward that, even though your flux is increasing, the sign of your current is decreasing. When you're moving away from it, the flux is decreasing, but the sign of the current is positive. Okay? And that's because it's the negative of the time rate of change. So I wanted to point out that wasn't just a happenstance there. They did that on purpose. Okay? If a circuit contains N tightly wound loops, now you're increasing the number of loops big time. Okay? And the flux changes by delta phi sub b, that's the magnetic flux. During the time interval delta t, the average EMF induced is given by Faraday's law. And here's Faraday's law. E, standing for EMF, that's an epsilon, I think, is equal to minus N, that N coils that you have there, d phi dt. D phi sub b dt. Delta phi sub b delta t. Okay? So the induced EMF is equal to the negative of the number of coils times the time rate of change of the flux change. Time rate of change of flux. That's Faraday's law, given at the top of page 660. The change in the flux, delta phi, can be produced by a change either in B, the fields, the magnetic field, in A, the area of the coil, or in theta, the angle between the coil and the field lines. Since the flux, magnetic flux, phi sub b is BA cosine theta. Okay. Now the negative sign of Faraday's law is included to indicate the polarity of the induced EMF, which is found by Lenz's law, and here's Lenz's law. Now we haven't mentioned who Lenz was. If my memory's right, I believe he was a Polish scientist, but I'm not absolutely certain of that. Okay? The current caused by the induced EMF travels in the direction that creates a magnetic field with flux opposing the change of the original flux of the circuit. Okay? So, God, my eyes are just stinging on me. So basically what it's saying here, remember, a moving charge induces a magnetic field, remember? Way back. Moving charge induces a magnetic field, okay? Well, this is saying the current caused by the induced EMF travels in the direction that creates a magnetic field, moving charge creating a magnetic field, with flux opposing the change of the original flux through the circuit. So basically, let's go back to this picture. I don't know if it's helpful or not. This is increasing the flux. moving it in this way. So the current here moves in a way to create a magnetic field that opposes that, okay? And that's why the negative is in there. And when you take this away, then the magnetic field in the coil is so it opposes that change and is trying to increase the flux. The flux is decreasing this way, so it's trying to increase it that way. So that's why the negative thing is there. It's a lot like Hooke's law with springs. If you pull the spring this way, you pull the weight this way, the spring pulls back this way. If you compress the spring pushes back that way. It's always opposite. Same type of thing here too. Okay? So that's Lenz's law. Okay? Here's an example, and this is in figure 20.5 on page 660. The magnetic field B, which is heading upward through this ring, coil, whatever you want to call it, becomes smaller with time. B is decreasing. It started with a large B that went to a smaller B. Okay? So that, since you have a changing magnetic field, you're going to induce a current. Okay? Now, what direction would... Goodness, my eye is hurting. What direction would that be? The magnetic field B becomes smaller with time. That reduces the flux. Okay? And if it's reducing the flux, then it's creating a current, of course, but that current, induced current, will produce an induced field, B induced, okay, there, in the same direction as the original field, because that field is decreasing, so this is trying to go in the opposite direction. So to do that, you need the B here to induce a current like that. The B would still be in the same direction. The induced current will produce an induced field, B induced, in the same direction as the original field. And it surely enough does. However, if you had a small b to begin with, and it was an increasing b, then it will create a b in the opposite direction to counter the increase. Okay? So it's always trying to counter the change. That's why it's a minus sign. Okay. Now, this ground fault interrupt is going to show up in a couple pages. Let's see what we've got first. First, let's do quick quiz 20.1. And let's see if I can find this figure anywhere. I don't think I can. Okay, I'll try to draw the figure here. This is your field strength here, magnetic field strength there, and here is your time in this direction. Okay? Here is point A, value B, and these are time values, and value C. Okay? Around A, we've got a constant field strength. Around B, we have an increasing field strength. Around C, we have a, whoops, I have it too much. Let me see if I can get this to do a little bit better. A slightly decreasing field strength. I probably still don't have it quite right. Okay? So here's A is constant, B is increasing, and C is decreasing. Okay? Figure 20.6 is a graph of the magnitude of B versus time for a magnetic field that passes through a fixed loop that is oriented perpendicular to the plane of the loop. Rank the magnitudes of the EMF generated in the loop from largest to smallest at the 3 instants indicated. Rate the magnitudes of the EMF generated in the loop from largest to smallest. Okay, let me correct this one more time. to make it a little more obvious. Yeah. Okay. Which of these, it says from smallest to largest, rank the magnitudes of the EMF generated in that loop from largest to smallest. No. From largest to smallest. Okay, sorry. Which of those will produce the greatest EMF?
Sorry, I didn't hear you.
Which of these three will produce the greatest EMF?
The top one?
Okay. We're talking about this one right here. The one I drew. A, B, or C?
The greatest EMF.
Huh?
You said DMF?
EMF. Electromotive force is what that used to stand for. They just call it EMF now because it's not really a force, but we still call it EMF. Wait. Say again? B is the greatest because this is the greatest rate of change. See, it all depends on the rate of change of your magnetic field. That's the greatest rate of change, therefore that will be the greatest EMF. Next. C next, because it doesn't matter the direction, it said magnitude. That's not quite as steep as this one was, so that would be the next. And of course, A is how much?
That's, it's flat.
That's 0. Yeah, there's no current produced then. I mean, no EMF produced then. So this is 20.1. Okay. Are you too disappointed about losing relativity?
No.
Okay. So this is BCA. You're perfect. All right. Faraday and Lenz to the rescue. There's a good example there, 20.2. And then what we just talked about is finding the direction of the induced current. I think the last couple of slides showed that okay. Let's see if we have these other two in there. No, we don't. Okay. All right. They have three examples here in the text, example 1, 2, and 3, and each of them has a figure with it. The figures are not super difficult, but you know it would take a while to draw those. But I would definitely read through those three examples. Okay. The first of these shows a long straight wire going with a current going up. Okay. The current, since that's a moving charge, induces a magnetic field. Right-hand rule. Put your thumb in the direction of the current, and your fingers point in the direction of the magnetic field. So you have a magnetic field produced. As the current I, the thing going up, increases with time, not stationary, but increases with time, so does the magnetic flux that goes through a coil. This other coil is sitting up here by the side. So here you have a long wire here with the current going up, increasing, and a coil over here that the field lines are cutting, and they're increasing the field strength. Okay? The question is, what is the direction of the, is there an induced current? Okay, you have a current moving up a wire, increasing as it goes up. You know, it's increasing with time. Over here you have a loop of wire. Okay? As this is increasing, it's increasing the magnetic field around it like this, and an increasing field, does that produce a current in this wire, in this loop?
Yes.
Yes, it does. Okay? So, which direction is the current flowing in that loop then? Okay? Well, if you have increasing field going in this direction, okay, got to get my right hand turned in the right direction here. The current is going to try to counter the increased current. Okay, the field is going like this. Right hand rule, right? Right? The right hand rule, the current's going like this, the field is going like this, the current's going like this, field's going like this, increasing. Well then, in this wire, the current's going to try to go in the opposite direction to create a field in the opposite direction of the increase. So it kind of tries to cancel it out. The induced current IR creates a countering positive magnetic flux. Okay, the second figure. This is Lenz's law, example 2. You have a magnet. Now this is more like the one back here. Let's go to this one. This one. Okay? We have a magnet moving toward a ring. Okay? Now it's not hooked to an ammeter now, but it's moving to a ring. As the magnet moves to the right, now they have it going in the opposite direction from this one. But as they have the magnet moving from, to the right, the positive flux increases through the coil. Okay? If it increases through the coil, then the current induced in that coil is going to try to go in a direction to create a field in the opposite direction. Okay? So therefore the current would be in the opposite. Now let's look at Lenz's law number 3, bottom of the page. The turns of a solenoid, you see it around just a paper tube or something like that. The turns around the solenoid create a magnetic field okay. What we have is an EMF, a voltage source, that's supplying voltage to this coil of wire, which is like an electromagnet or a solenoid. It has turns that will create a north pole to the left. Okay? North pole to the left because the coils are running like this, so the north pole would be pointing toward the left. As the positive flux increases, the induced current is clockwise, the induced current would be clockwise, trying to produce a field that's counteracting the changing field that you originally had. Okay? The electric field, opposing the magnetic flux. Opening the switch causes a rapid decrease in the magnetic field, and okay, you almost have to see it to believe it, okay, to follow it. All right, let's move to quick quiz to 20.2. A bar magnet is falling toward the center of a loop of wire. Okay, it's just falling, bar magnet falling, with the north pole oriented downward. So it's falling that way. Let's see if, I don't think we have a picture of that, do we? No, I don't think so. Nah. Okay. So a bar magnet is falling toward the center of a loop of wire with the north pole oriented downward. Viewed from the same side of the loop as the magnet, as the north pole approaches the loop, what is the direction of the induced current? So the north pole is going down through the loop. Okay? The magnetic field lines are increasing going down, so that is going to try to, the field lines are in that direction, so your let's see, make sure I'm doing the same thing. Viewed from the same side of the loop as the magnet, North pole approaches the loop. What is the direction of the induced current? Okay, so this is going downward. You would maybe think that the induced current would be in this direction. No. The induced current is in the opposite direction because it's trying to create field lines that counter that increasing magnetic field. So it would be, looking down at it, it would be going, I think, in a counterclockwise direction. Okay? And that says that would be C. A would be clockwise, B would be 0, C would be counterclockwise, and D would be along the length of the magnet. No. Okay. So you think 20.2 C, we think. Yes, 20.2 C. All right. .3. Two circular loops are side by side and lie in the XY plane. Two circular loops are side by side like this, lying in the XY plane. You get the idea? Like this, side by side. Okay. A switch is closed, starting a counterclockwise current in the left loop. Okay? That would be the one over here. The left loop, switch is closed, starting a counterclockwise current in the left loop. From your viewpoint, that would be this way. Okay? Which of the following statements is true of the right-hand loop? The current remains 0, and induced current moves counterclockwise, and an induced current moves clockwise. Okay, two circular loops are side by side in the XY plane. The switch is closed, starting a counterclockwise current in the left-hand loop as viewed from a point on the positive z-axis passing through the center of the loop. Which of the following statements is true? The current of the right-hand loop. Current remains 0? I think not. An induced current moves counterclockwise. This is going, no, the first one's going even counterclockwise. So I think it would be an induced current moves clockwise. Okay? Let's see, 20.3. Nope, it's counterclockwise. B. All right. Now the discussion about a ground fault interrupt. Are you familiar with what these are? GFI, ground fault interrupt. Okay. You said you're in an apartment now, right?
What did you say?
Are you in an apartment now?
Yes.
And you're moving back home next week?
Yeah, I'm moving back on Monday.
Okay. Now, it should be that in that apartment, if there's an electrical outlet in the kitchen, anywhere near the sink or the countertops where you'll be doing a lot of wet stuff, is there a receptacle there and it has 2 or 3 little buttons in the middle of it? One says test. Huh?
You said next to the sink?
Near the sink. Somewhere near the sink.
Not that I've seen.
Not that you've
in
seen.
my house, yeah.
In your house, yes. Yeah. Okay. Maybe the apartments were not built according to code, depending on how old they are. But your house is relatively new, or has been updated, or?
My dad's house is new, like. It's 2 years. It was built like 2 years ago.
Oh, I see. Oh, yeah. Well, then
Yeah,
you would have
yeah.
put GFI in. And I bet you in the bathroom you probably have at least one outlet that has GFI, ground fault interrupt.
And it says test, or does it say reset?
Yes, it has that little button that says reset.
Yeah.
And there may be one saying test. I don't know
I
about
think so.
that.
I think
Test and reset are the two I remember. Okay? If you have any outside plugs, they should be ground fault interrupt because rain could get on them and stuff like that. Do you know if you have any of those outside?
I don't know.
Okay. Check and see if you, I bet you do. Sounds like you have a new house that's fairly well up to date. Okay. Here's how it works, basically. Okay. The ground fault interrupter, GFI, I've always called it ground fault interrupt, is a safety device that protects against electrical shock. Wire 1, this one, leads from the wall outlet to the appliance. Okay? Wire 2 leads from the appliance back to the wall outlet. We usually call that the ground. The iron ring confines the magnetic field, which is generally 0, because usually it's fairly steady current moving in and moving out, except, notice this, these currents are going in opposite directions. So that's why the magnetic field is generally 0. However, if a leakage occurs that you have more current going in than you have coming out, then the field is no longer 0, and the induced voltage triggers a circuit breaker shutting off the circuit. This is your the coil around here. If this is fairly constant, this iron ring has a constant flux, basically. In other words, the current going out, in going out, basically cancel each other out. However, if they don't, if suddenly there's more going in because there's a leak somewhere going out, then this senses a changing magnetic field. That changing magnetic field then breaks the circuit breaker, and that's where your reset button pops out, and you have to push it back in to get it to work. Now, I don't know, you may be too young to remember, but I remember, you even know who Alfred Hitchcock is or was? Okay, he made really scary movies, but fun movies, you know, The Birds, The Rear Window. He made a bunch of really suspenseful movies, okay? And his genre that he's kind of started, but everybody else followed it, one of the favorite plots to knock somebody off, especially a spouse or something like that, is when they were in the tub to drop the battery, to drop the radio into the tub, or the hair dryer or something else, and make it look like it was an accident and the person gets electrocuted. Oh, and then you're so distraught, okay? Well, with the GFI, just as soon as that goes into the water and you get current going in one direction but not in the other, breaks the circuit just like that. So basically, supposedly, that would fix it so no one could get electrocuted in the shower. If it was plugged into a ground trough or into a tub or a sink, if someone was shaving with an electric razor, okay, and had a sink full of water in there, and it drops it and they reach down to get it, rather than getting electrocuted, it breaks the circuit, just like that.
I just want to turn these in.
Pardon me?
I just wanted to turn these in.
Just wanted to what?
Turn them in.
Oh, okay. Okay, so those are your ground fault interrupters. All right. Other applications of Faraday's law. In addition to everything else, he was big on electric guitars, huh? He wasn't, but he's led to them. A vibrating spring induces an electric field in a coil, okay? So if you have a string here and somehow affix it so you have a part of this magnetized, a north and a south, okay? If that's a guitar string, okay, and you pluck the string and this is moving in this direction, then you're creating a current that can be picked up here. That goes to the amplifier, and that's why electric guitars can give you that, you know, the sound going up and down in amplitude, just because of that string. Now, I don't know where. I guess these are actually little magnets under here, and that changing the pattern there does create. That's what goes to the amplifier, and so it's not just the tension on the wire that produces the sound. It's the amplified by the fact that you have changing magnetic current, and that increases or decreases the amplitude. So that application is electric guitar pickups. Vibrating string, so I did finish this, induces the EMS in the coil. Okay. A permanent magnet inside the coil magnetizes a portion of the string nearest the coil. So this is what magnetizes the string. Okay, just a little bit of it. Okay, making this a south and that a north. That strong permanent magnet there, and that's what you see here. That's the ends of those permanent magnets there, one for each string. Okay, and these are steel cores, so they can be magnetized. It's a temporary thing. Permanent magnet magnetizes. As a string vibrates at some frequency, its magnetized segment produces a changing flux that's picked up by this coil here. Not by this magnet. The magnet just happens to be hanging there, okay? But the coil picks up the changing from that string, okay? The changing flux produces an induced EMF that is fed to the amplifier, and then that amplifies the sound even more, okay? So pretty good setup. You get a lot more sound out of the electric guitar than you would an acoustic. Of course, I like the sound of an acoustic better. Another application of Faraday's law. This is on the bottom of page 664. Okay? The coil of wires attached to the chest carries an alternating current. Okay? An induced EMF, this is an apnea monitor. You know what apnea is, right?
I know what sleep apnea is.
Yeah, that's what they're talking about.
Okay.
Yeah, and this is in a baby that seems to be exhibiting that. The coil of wires attached to the chest carries an alternating current. Nothing that's going to shock the child at all, okay? The induced EMF is produced with varying field passes through the pickup coil. Well, what would be a varying field? When the breathing stops, the pattern of induced voltages stabilizes, the external monitors sound an alarm. So as long as the breathing is going on there and you're changing the field, then it's fine. It's happy with that. But as soon as that stops, then it sounds an alarm, an alert, and sometimes that's enough to wake the baby and he starts breathing again, or it alerts the mom that she needs to come in and check on the baby because he's briefly stopped breathing. Here is another application of Faraday's law. It's motional EMF. Okay? What we have here, this setup here, if you can see it, just to give you an idea. Now, since no one's in the room, I won't point to the board, I'll point to this. A straight conductor of length L, that's this conductor right here, okay, of length L, moves perpendicularly through with a constant velocity, that's that velocity v there, through a uniform field. The field is into the page. That's why you see the arrows, the tail of the field lines, magnetic field lines sticking out. So that means the field is into the page. Okay. the electrons in the conductor experience a magnetic force. You've got a velocity in this direction, a field in that direction, and your force is QVB. Okay? Q is the charge that's sensing this. V is the direction of the velocity, and B is the magnetic field strength, and QVB is that electric force. Magnetic force. The electrons tend to move to the lower end of that conductor because the force is in that direction. The electrons tend to move opposite the force because they're negatively charged. So your magnetic field, you do say, a force there, and it's sort of like creating a little battery with an EMF there, with a positive at the upper end and negative at the lower end. Okay? As the negative charges accumulate at the base, the net positive charges exist at the top of the end of the conductor. The result of this charge separation, electric field is produced in the conductor. And there's the force is down, the field line, and they used to do that in, I think blue. So this is also the electric field line there, okay? And it's perpendicular to the magnetic field line, also perpendicular to velocity, okay? Charges build up at the ends of the conductor until the downward magnetic force is balanced by the upward electric force. So they didn't include anything here. You'll have to go back to the previous chapter, chapter 19, to check on your magnetic force. So I think I'll quickly turn back there to give you a reference to it. Okay, 19.5, I believe it is, magnetic force on a current carrying conductor. Looks to be about the stuff that's on page 630, and it shows the electric force in this case. What you're doing is moving the rod, not bending it, and so it's not quite the same thing, but the electric force is downward, the field is downward, and what I can't, I said the electric force, is that forced by the magnetic field. If you're moving charges are that way, the field then is this way, so it opposes that field, so it's coming out. The force is coming out. I think there we go. 2 pages over. So that's your motional EMF. Okay, the charges build up at the ends of the conductor until the downward magnetic force is balanced by the upward electric force. There is a potential difference between the upper and lower ends of the conductor, and that's what we saw there. Plus is at the upper end, minus at the lower end. and that then sets up a magnetic electric force, the field lines down, and the force due to the magnet is also down, but the hard to say why that they have that force down. And called it a magnetic force. I would call it an electric force. Well, decided to come after all, huh? Let's see, are you in here? You just made it. I mean, by the skin of your chinny chin and the hair of your chinny chin or something like that. All right, just to let you know what's going on. Try to keep this as quick as possible, but I'm running out of gas late in the day. The end of last week, I had to spend getting ready for a big meeting we have tomorrow, a big report. It's called our planning hearing. And I had requested the data from my instructors back in June, and most of them had responded, and I was putting together, compiling the results, but one never responded. I called him last week and finally got an answer on Thursday that he said he would get me the result on Friday, which was very convenient because Friday was supposed to be my day off. I was able to work on it a little bit Friday and mix it with the others, finish it up over the weekend, but he still didn't send the documentation, which I have to have too. So I have to go over in the morning to the Birmingham campus around 7:45 or probably earlier to get together the packet with the documentation he's supposed to provide. I have everything prepared except his documentation. Our hearing is at 10, and it'll go till 11, but then I have another hearing I've got to participate in from 11 to 11:30. 11:30 I come back to this campus and teach a 12 o'clock class, and then it goes until 3:30. And finally at 3:30 I've got some office hours I can actually do work, like grade papers and do that. I haven't had a chance to do a bit of that over the weekend. I was working on that planning here the whole weekend when I had time. I didn't have much time this weekend, but all the spare time I had, I couldn't grade papers. I had to do that. So therefore, if you turn in anything and haven't seen it on Blackboard, that's why. I may have gotten a few things graded, but nothing put on Blackboard. And I'll try to work on that tomorrow afternoon. I say I'll try because I already know one student's coming in to work to find out about a research project. That's going to take a chunk of time. I probably am going to have some other students who couldn't get to me today come in for advising, academic advising. That's happened just about every time I've been in the office this last couple of weeks. And I've got some tests to finish working on and things like this. So I have tons of stuff to do in that little hour and 45 minutes that I have in the office tomorrow afternoon, because I've lost all my office hours in the morning. Now, if I get everything done in the morning, I may be able to grade a few papers in the morning, but that's about all I can hope for. So, anyway, it's that's why you will not have seen it. It's also why, because FA has to be leaving early, so she has to take her test early, and if we were going to stay in Chapter 26, then I would have to get that test ready before Wednesday, which I only have a short time tomorrow afternoon in the office with lots of other competing things. Whereas Chapter 20, what we've done is go back to Chapter 20, and the last test will be on 20, not on 26. You've been exposed to the relativity, that's all you get. We're going back to 20 because I already have this lab made out and the test made out. I just have to run them off. So that's where we're sitting. That's why we're in Chapter 20 now rather than 26. We made that decision early on. Okay, So this is called motional EMF. There's a potential difference between the upper and lower ends of the conductor, as we saw in the picture. Now, the potential difference between the ends of the conductor can be found by your delta V is that electric field strength times L. Okay, remember, E is equal to delta V over delta X, basically, type thing. And so delta V is E times L. What is the E but V times V? Okay? Now, those look like different L's to me. I don't know if they're supposed to be or not. I don't think so. Yeah, they're the same. They just didn't look like the same. The upper end is at a higher potential than the lower end because the pluses are high and the minuses below. The potential difference is maintained across the conductor as long as there is motion through the field. You stop the motion, the charges go back. If the motion is reversed, the polarity of the potential difference is also reversed. So, let's go back to the picture again. As long as this is moving this way, it's forcing charges, negative charges down, positive charges up, as long as it's moving this way. If you stop, they go back. Okay, just being in the field isn't enough, they have to be moving in the field. If you reverse the velocity and move it back this way, then the negatives are moving up and the positives moving down, and you have the reverse going on. Okay? So there's only a potential difference when the conductor is moving. If the conductor stops, the potential difference goes away. If the conductor reverses its direction, the field is produced in the opposite direction. All right, so here's motional EMF in a circuit. All right, what we have here is that length L between these, that's the length basically between these two plates. They are just bigger than wires. This is a wire, this is a conductor that slides along. Okay? Assume that the moving bar has zero resistance. In other words, this is very well lubricated between the bar and the plate there. There is no resistance. They're slick, 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 and there's no resistance. So assume that both the bar has zero resistance. As the bar is pulled to the right with a given velocity, so you're applying the force in this way, giving it a velocity in that direction, under the influence of an applied force, the free charges experience a magnetic force along the length of the bar. The free charges that are in the bar, this is a conducting bar, the free charges experience a magnetic force along the length of the bar. Okay? That force sets up an induced current because the charges are free to move in the closed path. So you see you have a closed path here and you induce charges to move, but now they just don't stay on the bar, you have a path that they can follow. So if the pluses are going here, they're going through a resistor here, coming back here to the negatives, so they can keep moving in this direction. So you have current flowing in the counterclockwise direction, as long as the velocity was this way, okay? Because the magnetic force is trying to resist that and pull it back in the opposite direction, okay? The force sets up an induced current because the charge is free to move in the closed path. Magnetic force F sub M opposes the motion, and a counterclockwise current is induced. So this is the force V cross B. That would have the charges moving up in this direction. The magnetic force, though, would be opposing that movement. Okay. Again, a lot like Hooke's law of spring forces. Now, the changing magnetic flux through the loop and the corresponding induced EMF in the bar results in a change in the area of the loop. Because you're pulling it that way, now you're cutting more field lines. So you have a changing magnetic field as well. Okay? The induced motional EMF acts like a battery in the circuit, and actually you get loading in the resistance if you need it. Okay? So the magnitude of that EMF is E, that's the magnetic field strength, L, that's the length of this, B, the velocity in that direction has two things to it. It has a velocity, a length in that direction that's changing, delta x, and it also has a delta t, and that's the time rate of change of that field strength. So, the current then is its monochromatic electromotive EMF, electromotive force, is VLB from that, and then the current is force divided by resistance, so it's VLB divided by R. This resistance here, and that's the amount of resistance, and as we said, as long as it's moving that way, it will be in the opposite direction. Because the current flowing that way is trying to counter the field, increased field lines that you have the other way. Whew. I'm running out of juice. Okay, that was motional EMF. There is an Applying Physics 20.2, which to me really looks interesting. The space catapult. I've heard people talk about this before. I think they do a pretty good job of describing it. I don't know if it's good enough for you to follow, but it is a pretty good one. Quick quiz, 20.4. I think we did 2 and 3 last time, didn't we? Yeah. A horizontal metal bar, oriented east-west, drops straight down in a location where the Earth's magnetic field is due north. Okay? So let's do, this one's dropping down here where the field lines are due north. As a result, an EMF develops between the ends. Which end is positively charged? Okay? So your field line is this way. Your velocity is this way. Which way is the, which end is positively charged? Okay? Magnetic field line's this way. The bar is moving this way. One end of this is positive charge and one's negative. Okay? And let's get this. If that's north, this is east, that's west. So the answer is going to be east or west. Okay? Which is it? The east end, the west end, or neither end carries a charge. I think we can rule out C, right? One end is going to be charged. You can set this up like the picture on page 665. Let me go back to it. This one. Okay. Now you get velocity downward. The field lines are that way, so you're now looking at it fall that way. Flip that over, kinda, and that would make the east end, it looks like, positively charged. Okay, see, the east end should be A. 4 is indeed A. Okay? You intend to move a rectangular loop of wire into a region of uniform magnetic field at a given speed so as to induce an EMF in the loop. The plane of the loop must remain perpendicular to the magnetic field lines, whichever they are. In which orientation should you hold the loop while you move it to a region where the magnetic field is to generate the largest EMF? With the long dimension of the loop parallel to the velocity vector, the short dimension of the loop parallel to the velocity vector, either way will cause an EMF is the same regardless of orientation. I think we can rule out C again, okay? I believe so, but let's check it again. You intend to move a rectangular loop of wire into a region of uniform magnetic field at a given speed so as to induce EMF in the loop. The plane of the loop must remain perpendicular to the magnetic field lines. In which orientation should you hold the loop while you move it into the region with the magnetic field to generate the largest EMF? With the long dimension of the loop parallel to the velocity vector, or the short end parallel to the velocity vector? It just seems like to me you want the the velocity vector this way. Seems like to me you would want the short dimension parallel to the velocity vector, so the long dimension would be perpendicular to it. So I'm guessing B there. 20.5, sure enough, is B. All right. Example 20.3 is potential difference induced across airplane wings. That can be a little frightening if you set up a battery across an airplane wing. And whereas the energy source, that's example 20.4, which I think is a pretty interesting problem too. If you're sliding a bar, then the energy source is the energy that's moving the bar. Okay, basically. So now I think we're ready finally for generators. And again, who's responsible for generators? I think the earlier slide said Michael Faraday. Yes, you got it. Faraday. All right. And usually when they say generators, you think AC, alternating current. If you want DC, you think batteries or power supply or something like that. But alternating current generator, creating an alternating current generator. It converts mechanical energy into electrical energy. Okay? It takes the mechanical energy, the water turning the turbine at a hydroelectric plant, the steam turning the turbine at a coal-fired or natural gas-fired or nuclear-produced plant. You're heating, some way you're heating the water, creating steam, very high temperature, very high potential. That's your mechanical energy, changing it to electrical energy. Consists of a wire loop rotated about by some external means. Guess what? It's going to be more than a wire loop. It's going to be probably bunches of wire loops. There are a variety of sources that can supply the energy to rotate the loop. As I was saying, boiling water in a hydroelectric plant, heat by burning coal, natural gas, or something else to produce steam. The steam then turns the turbines. That's your kinetic energy. Or nuclear power is heating the water, creating the steam that's turning the turbine. Okay? You've just got to have heat to produce steam, and the steam flows and turns the turbine blade. Okay. Now, basic operation of this AC generator. As the loop rotates, okay, you've got something turning it. Something is making that turn. Okay? When you're turning the loop, and by the way, that loop is in between is in the presence of a strong magnetic field. Two permanent magnets there, north end, south end, okay, north pole, south pole. Fixed in place, you're turning the loop. So if this is well designed north and south, you have basically a uniform magnetic field pointing from north to south, right? There's your magnetic field, all right? Something is making that loop spin. Water, steam, something is making the loop spin, okay? It could be a wind turbine. The wind could be making it turn, okay? You just got to have something creating the motion. As it turns then, notice that one end of one of these is on an outer ring, the other end on the other is on an inner ring. These are called slip rings, okay? Now there are also brushes, and I really do not understand what they mean by brushes here. I would have said the brushes are at the end of this, brushing on the rings there. But they're showing the brushes as being external to the ring, as if the ring itself is turning. And that seems to be a bit bizarre, but whatever, because they call them slip rings, you wouldn't think they'd be turning. So I find that drawing a little bizarre, but I guess it's true. Okay? As the loop rotates, the magnetic flux changes with time. Like the orientation, you see it right there, is cutting close to the maximum number of field lines, right? And as it turns, and it has it turning, looking this way in a clockwise direction, as it turns then, looks like it may cut a few more lines, but then it starts decreasing the number of field lines that it's cutting until it gets horizontal here. Then it's cutting no field lines, okay? So you're going from maximum to zero. So that's sort of like following a cosine curve, starting at +1 and going to 0 as it turns there, okay? And then when it turns again, past the 0, now it's cutting field lines, but the other side is doing, so you're reversing direction. It went from some positive number decreasing down to 0, now to a negative number, and this is creating an alternating current coming through here, okay? It's negative, increases negative until it gets oriented reverse from what it was to begin with, and then it's cutting the maximum number of field lines. That's going to be your maximum or your minimum negative current, and then it's going to turn another halfway around, quarter turn, and you're going to line up to 0 again. So what you're doing is creating alternating current. EMF is induced in the coil, which rotates by some external means of a magnetic field. That's basically what it is, a rotating coil in a fixed magnetic field. So the loop rotates, the magnetic flux through it changes with time, change in flux creates a current. This induces an EMF and the current in the external circuit. The ends of the loop are connected to a slip rings that rotate. Okay, so the slip rings do rotate with the loop. Okay, just the name slip ring made me think they stayed still, but they're rotating too. So therefore, the brushes here, that sort of makes more sense. Okay. Connections to the external circuit are made by stationary brushes in contact with the slip rings. And these, I guess, then are the brushes, and they stay in contact with the slip ring. But they probably have fine little cilia underneath them, the brush part, the thing, so you don't have friction there. You just have the brushes. And sure enough, that's what sends the current through the light running it. Okay? With no battery whatsoever. You're generating it using that fixed magnetic field, and you're changing the flux through that coil. The EMF generated And I would have started with the +1 because that's how they showed the picture. EMF generated by a rotating loop can be found by E. The EMF is epsilon is equal to 2BL V perpendicular, which is seems like to me they left off a V. Let me see. I can't believe. Yes, they did. This is equation 20.6 in your book. 2BLV perpendicular, which is 2BLV. There is a V there times the sine of theta. Okay. Now, if the loop rotates with a constant angular speed of omega and n turns, so now we have n coils, that would be for one coil, you now have n turns. Now you have NV. Now L times V gives you A divided by T, okay, because V is a dimension divided by T, and L is perpendicular dimension to that, so L times V would be an area. But divided by T, that would be your omega, and then that is times the sine of omega T. Okay, so now the A has incorporated the L and V. So I'm just going to say we left off the V again, but no, it's incorporated that. Now, NBA, number of coils, magnetic field strength, area, and then your angular speed. When E is equal to E max, the very highest that voltage can be, when the loop is parallel to the field. Okay. Now, when they say parallel to the field, what do they mean? The normal line is parallel to the field. That makes the loop perpendicular to the field. That's one thing that's so hard to realize when they say that. When E is equal to 0 and the loop is perpendicular to the field, meaning the normal to the loop is perpendicular to the field. Remember, they're always talking in terms of the normal. And this would give you your current, field, voltage, EMF. Okay, here is a little detail on that rotating loop. The magnetic force on the charges in the wires AB, that's this one, okay, and CD, that's the one over here, is perpendicular to the length of the wires. The magnetic force on the charges in the wires AB and CD is perpendicular to the length of the wires. And EMF is generated in wires BC and AD. The EMF produced in each of those wires is E is equal to BL V perpendicular, which is VL, and again they left off the V. So what their problem is here? That again is missing a V. Okay, V sine theta. Okay. All right. Now, what in the world is a DC generator? It looks a lot like an AC generator with one exception. The components are essentially the same as an AC generator. The major difference is the contacts on the rotating loop are made by I'm sorry. Made by a split ring, or sometimes called a split ring commutator. And here's the story on this one. Okay? Right now, Right now, you have almost the maximum field lines being cut. Not quite, it looks like it's tilted a little bit. Something is forcing this to spin. Water, steam, something. Okay? Forcing it to spin. Now, that's almost cutting maximum field lines. Okay? And it's going to start decreasing the field. It will increase as it turns a little bit more. Then start decreasing the field lines. Decreasing, decreasing. Until it gets here to 0. And then it would have gone and started going in the opposite direction. Like AC. Except that's where you jump the gap here and here. And now the end that was here turning is over here. This end up here is turning and is down here. When it jumps the gap, then this one's let's say, just for no other reason than that. Let's just say the current is going in this direction here. Okay, going around like this. And then right about the time it gets here, it's starting to change direction of the current. And this one would be then go negative, because it's going to 0 here. It's going to go negative. But as soon as it jumps there, it goes to the other side, and the negative's down here, and this one's, the other one's now positive. It goes up here. So it sends a positive half pulse. So every time around, it's a positive half pulse, and then the reverse direction, and goes back to a positive half pulse. Okay? And what you have then is a pulse DC, direct current generator. Major difference in the context of the rotating loop or major split ring commutator. So let's see if they show, yes, and this is what your pulse looks like. And in AC, it would have been positive, positive, max, decreasing, decreasing, but still positive, go to 0, and then go negative. But as soon as it would go negative, then they switch poles, and that one becomes positive. They go in the opposite direction. And as soon as that one was starting to go negative, they switch poles again, and the other one is positive. So you have a direct current generator. Now, it's not a steady direct current. It's a pulse direct current, but always the current is in the same direction. The output voltage always has the same polarity. It's showing positive. The current is in a pulsing current, and to produce a steady current, what they do is have many loops and many commutators around the axis. So, get this. The next one would be doing like this, and then you have another one that's putting the gap between those, and then again and again and again. So basically you're filling up something that's almost constant, very, very close to constant. Many loops and commutators all around the axis of rotation. The multiple outputs are superimposed, and the output is almost free of fluctuation. It will have a little bit of waviness, but generally nothing that can't be smoothed out electronically really easily. Okay? Now, there is an example that goes with that. Okay, what do we have? We started at 5:30, went to 6:20. So we're technically in lab time now. So if they manage to stay long enough to get to lab time, and Samuel just barely got here by lab time. Okay? So it's just you and me. Okay. Do you want to just keep trucking right through? Do you need a little break? No break at all? Okay. Okay. If you don't mind, I just need to run and get some water. I've been talking for, well, actually. Okay. We finished basically generators. Now let's move to motors. Now this is 20.4 on the old slides, but it's 20.4.1 on this section. 20.4 was generated, and 24.1 is motors and back EMF. Yeah. Okay. So motors are devices that convert electrical energy into mechanical energy, basically, and literally, I think this was the first one to happen. I may have to go again because the train is really getting to me here. But folks had figured out how to generate electricity using generators, okay? And it was a fairly new technology. People had begun using it and didn't have that many applications for it yet, but they could show that the process worked. And they were showing this off at a World's Fair, and I don't remember where. It seems like it may have been St. Louis or somewhere, but a World's Fair. And the guy went to, a technician was setting up the display to show how to generate electricity. Now, this is what I've heard. Somehow the story seems like it has a few things wacko in it, but supposedly it happened. What he did, he got two wires backward. And when he went to do it, he actually set up a motor, an electric motor, because literally a motor is a generator run in reverse. Now, the only thing wrong with that story is where did he get the energy to run the motor? I haven't figured that one out yet, unless he had a couple of them running and turned one in backwards, plugged it in backwards, and it started being run by the other one. And that was literally almost the first electric motor. A motor can perform useful mechanical work when a shaft connected to the rotating coil is attached to some external device. So whereas a generator, you have an external thing turning the shaft there and turning a coil in a magnetic field, creating current and voltage, then a motor, on the other hand, is the electricity turning a shaft that is doing work. So one is taking kinetic energy and converting to electrical, the other is taking electrical and converting it to mechanical. So let's look at motors and what they call back EMF. The phrase back EMF is used for an EMF that tends to reduce the applied current. It's a lot like what we had when we were creating a magnetic field. Creating an electric current with a changing magnetic field. The electric current that you generated tried to generate a magnetic field to counter the original one, the changes. So that's what basically your back EMF is doing too, is trying to counter what was changing otherwise, okay, to reduce the applied current. When a motor is turned on, there is no back EMF initially, okay? The current is very large because it is limited only by the resistance of the coil. There's the resistance, okay? But they're going to carry it forward now. So here we have, and that's a pretty small resistance too, 10 ohms, not very much, okay? So here you have a 120 volt external source that's turning a coil under resistance, and that's going to be doing whatever you need it to do. Well, a back EMF of 70, and they'll get to the numbers later, is virtually made here, I guess is one way to say it. Okay, it's not really an EMF there. It's called the back. Is the EMF that tends to reduce the applied current, because that's a lot of current will come out of that. Shoot, look at that. That would be 12 amps of current. That's a lot of current. You don't want to go around messing with 12 amps. That's really hot. Okay. So as the coil begins to rotate, an induced back EMF opposes the applied voltage, and the current in the coil is actually reduced. the power requirements for starting a motor and for running it under heavy loads are greater than for running the motor under average loads. And of course that makes sense. It's just like starting a car engine, except of course there you're doing a lot more, but it takes a lot of current to first get it going, and after that you've got plenty of current to recharge the battery. Okay? If though you run into a heavy load, then you need a bit more. I think of this, and it's a sort of a dumb thing. Usually on Saturday nights I trim my beard. Don't mess with it during the week, but I usually trim it on Saturday night. And I could imagine when you first turn on the electric clippers, and stuff, there's a rush of current. And then if I just ran them without doing too much, it would run for quite a while. But as soon as I start trimming, I can hear it go. I mean, it slows down. You're putting a load on it, so that's requiring more power when it's meeting that resistance. And then, unfortunately, it builds up in the head, and then I can hear it really start running down. I have to take it out and clean it and put on a different head so I can do a different kind of trimming. But you can basically hear that same kind of stuff go on. Now that's AC, not DC, DC, not AC. Okay. That leads to self-inductance. Did we finish that slide? I think we did, yeah. Okay. That leads to self-inductance. Self-inductance occurs when the changing flux through a circuit arises from the circuit itself. And that's basically what we just said before. When you had a lot of current going through that coil, then you're creating a counter current that is trying to diminish that. Okay? As the current increases, the magnetic flux through a loop due to that also increases. That increasing flux then induces an EMF that opposes the change of the magnetic flux. So you've got something against you. As the magnitude of the current increases, the rate of increase lessens and the induced EMF decreases. That decreasing EMF results in the gradual increase in the current. Okay? Now that almost sounds circular, okay? And it is in some extent. The self-induced EMF must be proportional to the time rate of change of the current. So that EMF is equal to minus L. Whoa, what is that L? Introducing a new term here. EMF is equal to negative L times the delta I of the delta T. Change of the time rate of change of the current. L is a proportionality constant called the inductance of the device. The inductance of the device. The negative sign indicates that the changing current induces an EMF in opposition to that change. So this EMF is changing the current, but that is inducing another EMF that's in the opposite direction. Okay. And that's your back EMF. The inductance of the coil depends on geometric factors. Okay? The SI unit for the self-inductance is called the Henry, named after, I can't remember what Henry's first name was. That was his last name. It wasn't Henry something. It was something Henry. And 1 Henry is 1 volt second per amp. Okay? Let's go back and see if that makes sense. Go back to the previous slide. This L is measured in Henrys. So what is that Henry? A volt. Notice here. A volt times a second divided by current. Okay? That would be what a Henry is. Volt second per amp. Volt second per amp. You can determine an expression for L, and that would be L is equal to N, that's the number of coils you have, times your, here we are at flux again, change of flux per change of current this time, not change of time, change of current. And if you had a constant change here, then that would be N P V sub E over I. Okay. Real tempted to go through the units there too, but that would get a little too confusing maybe. So let's move on. Here's Joseph Henry. By the way, your induced example 20.6 is an induced current in a motor. Joseph Henry lived 1797, which is basically just shortly after, who was the one just a few, was that Faraday? I think it was just a few years younger than Faraday, maybe 6, lived to 1878. Boy, he lived a pretty long life. That was 81 years, but back in that time, that was pretty good. He was the first director of the Smithsonian Institute. Amazing. Must have known that before, but I'd forgotten it. His first president of the Academy of Natural Science. Pretty impressive. First to produce an electric current with a magnetic field. Okay? Now let's see. Wait a minute. It almost sounds like, but I mean, he and Faraday were compatriots, except, of course, they were different. Henry was American, obviously, if he was here at the Smithsonian and Academy of Natural Sciences. He improved the design of the electromagnet and constructed a motor. He discovered self-inductance, things we were just talking about. So obviously a very bright guy. And he must have come along before Hertz. Why would I say that? Because the Henry got the capital H, but Hertz must have come along later, because then it became HZ, because H was already taken by Henry. Okay. So let's look at an inductor in a circuit. Inductance can be interpreted as a measure of opposition to the rate of change in the current. That's a pretty good way to look at it. Inductance can be interpreted as a measure of the opposition to the rate of change in the current. Remember that resistance is a measure to opposition to the current, period. And inductance is the measure of opposition to the rate of change of the current. As a current circuit is completed, the current begins to increase, but the inductor produces an EMF that opposes that increasing current. Therefore, the current doesn't change from 0 to its maximum instantaneously. It takes a while. Okay? And of course, remember, alternating current is not off ohm. It's a slowly changing or relatively slowly changing operation. So here is an RL circuit. Okay? Oh, there's your blurb on Joseph Henry. He was an American physicist, born shortly after the Constitution went into effect. Became first director of Smithsonian Institute, first president of the National Academy of Natural Sciences. Yeah, everything I think we just said. He was the first to produce an electric current with a magnetic field, but he failed to publish his results as early as Faraday because of his heavy teaching duties at Albany Academy in New York State. He improved the design of electromagnet. Okay, so it's almost the same type deal of Newton and Leibniz. He and Faraday were producing almost the same things, but Faraday was a bit quicker at publishing. So they think Henry may have actually beat him to some of it, but Faraday published first. Applying physics 20.3, making sparks fly. That looks like a pretty interesting one to read. and think through. And then example 20.7, inductive self-induced EMF in solenoids. So now we're to RL circuits, 20.6. Okay? A circuit element, an RL circuit is when the circuit reaches its maximum, the rate of change at the back EMF are zero. When the current ultimately reaches its maximum, the rate of change of the current and the back EMF are zero. Okay? Now you don't show the back EMF, but basically it is there. Now here's the odd thing about this. Okay? No, it's not really odd. It's okay. This is the positive side of the battery. Okay? Now here's something. This is a little on the odd side. I don't usually think of inductances in DC's current circuit. But they're showing it here as if it was. But that's an EMF. It doesn't have to be DC, but they're showing it as if it is. But if you had an EMF, give an EMF here, going through a resistor, you're going to drop a certain voltage drop across that. But then you get to your inductor, and the inductor slows things down. Okay? It makes it follow the rate of change of the current. You know, it sort of opposes that, but ultimately the current gets up to the level it needs to be. The time constant tau for an RL circuit is the time required for the current in the circuit to reach 63.2% of its final value. Now, again, I'm trying to remember that it seems like that is one standard deviation, basically. 63.2%. Something pretty close to that. Okay? Sort of an odd type unit there, but that's the time it takes for the current to reach 62% of its final value. Hasn't gotten there yet, but it's on its way. Okay? The current increases toward the maximum value, and that maximum value would be E over R. That ultimately is the maximum. Now, the time constant is that amount that it reaches 63.2% of that maximum value. Now, when it finally does go up there, now it acts just like the inductor wasn't even there. Okay? Your current and the resistance is kind of everything. Follow Ohm's law pretty well after that. But after the switch is closed at TH0, the current increases toward the maximum value, but it takes a while to get there. The time constant depends on both the resistor and the inductor. That time constant is L over R. Tau is L over R. The current at any time can be found by current is generally electromotive force, voltage, divided by resistance. But you have this extra factor in here from your inductor, that 1 minus e to the minus t over tau. What is t? What is tau but L over R? So you could say this is 1 minus e to the minus R over L. Okay? Minus RT over L. RT over L. That's the current at any time t. So, next topic, okay, sort of an abrupt change there. Before we go to the next one, however, let's do quick quiz 20.6. This is on page 676, okay? All right. Let me go back to this figure here. All right. I'm going to add a circuit element here, a light bulb. Okay. Okay, that's a light bulb. Pretty ugly light bulb, but it is. Okay. This switch is going to be closed. So go on and close the switch. Okay. And the one other thing is I'm going to have a piece of iron that is partially in the coil. Okay, the inductor. Okay. The switch in the circuit shown in this figure is closed. The light bulb glows steadily. The inductor is a simple air core solenoid. An iron rod is inserted into the interior of that solenoid, increasing the magnitude of the magnetic field in the solenoid. As the rod is inserted, the brightness of the light bulb, A, increases, B, decreases, or C, remains the same. What do you think?
The coil?
Okay. What you have here, the switch is closed. I just closed the switch down there. Okay. The light bulb glows steadily. That's the little blue thing over there. Okay. The inductor is a simple air core solenoid, but an iron rod is going to be inserted into that solenoid. Okay. Into the interior of that solenoid. It was just the surrounding air before. Increasing the magnitude of the magnetic field in the solenoid. The iron cord is going to do that. Okay? As the rod is inserted, the brightness of the bulb increases, decreases, or remains the same.
But the current's going this way, right?
What's that?
The current's going this way.
Right.
Closed switch. I say increase.
Okay? The only thing that I think is happening here, because that is increasing the magnetic field of the solenoid, I think that to begin with it slightly decreases because that's increasing the strength of the solenoid, of the inductor, and the inductor is reducing the increase of flow. Okay, that's what an inductor does. So I think temporarily it decreases until you get it in place, and then it goes back to the same brightness it was before. But I think it decreases first.
That makes sense.
Well, let's see if it does. Okay, this is 0.6 is B, which is decreases.
You're always right. I'm gonna use
Not always. Okay. All right, the next example here is an RL circuit, example 20.8. Well worth your time to take a look at that one, and followed by 20.9, which is formation of a magnetic field, which probably would address Quick Quiz 20.6 as well. And then we're ready for energy stored in a magnetic field. This is 20.7. The EMF induced in an inductor, induced by an inductor, prevents a battery from establishing an instantaneous current in the circuit. What it does is slows the increase of that current. Without an inductor there, it comes on, goes off. But the inductor prevents the battery from establishing an instantaneous current, but it just makes it more gradual. The battery has to do work to produce a current. That work can be thought of as energy stored in the inductor in its magnetic field, and that potential energy that you're storing there in the inductor, so it's an inductor potential energy, is 1/2 Li squared. Okay. And remember what a Henry was? That's what L is measured in its Henrys. It's a volt second per amp. So volt second per amp multiplied by amp squared. One of the amps goes out, and it's a volt times an amp. Voltage times an amp is power multiplied by second gives you energy. And sure enough, that's kinetic potential energy. Okay? The work can be thought of as energy stored in the by the inductor in its magnetic field. And that's why when you inserted the iron core gradually, you were increasing that magnetic field, so temporarily it was decreasing the current to dim the bulb a little bit. Whoa! That's all, folks. That finishes 20.10 magnetic energy. Okay? Wow. It's a lot quicker chapter than I thought it was going to be. Okay, the summary here is example 2010 is magnetic energy. It's a good example to follow up on that same thing. And by the way, just as a reminder, the potential energy in a capacitor is 1/2 the capacitance times the delta V squared. Okay? So notice there is a certain symmetry or similarity, anyway, of what you got there. The potential energy stored by an inductor is 1/2 Li squared. The potential energy stored by a capacitor is 1/2 C delta V squared. Okay? Pretty interesting parallel there. Okay? By the way, we just finished the chapter. I didn't think it was going to be that quick, but we did. And I was just saying that the summary here, 20.1, has a formula, illustration, and a good description of what's going on with induced EMF and magnetic flux. 20.2 talks about Faraday's law of induction and Lenz's law. It describes both of those, gives the formula for Faraday's law, and gives the verbiage of Lenz's law. 20.3 is motional EMF, okay, and it gives an illustration and a little bit of a definition. 20.4 is generators, and gives you an equation, a formula for it, and a figure that doesn't look a lot like the others, but if you think of that as a loop spinning, you got that. Then you have 20.5 self-inductance. They don't say too much with that. 20.6 is RL circuits, and they give you several formulas, a couple of illustrations, at least 4 formulas and 2 illustrations there, 2 figures. And then finally, 20.7, energy stored in magnetic fields is the formula is given there in a little bit of description. Then you have your conceptual questions, and I think the odd numbers for these are in the back, so any of those odd numbers would be fine, 1 through 13. Probably a few fewer than normal for just a short chapter. That's not too surprising. And then 20.1 is induced EMF and magnetic flux. You can do any of those odd number exercises 1 through 7. 20.2 Faraday's law, you can do any of those odds 9 through, there's a whole bunch of these, 21. And they show a patient in a hospital with whose breathing is being monitored by a coil. Okay. We showed one with a baby earlier. This is an adult. Motional EMF. There's any of the odd questions there, 23 through 37. No, 23 through 29. And then generators, 21 through 37. Self-inductance, odds 39 through or 41. Either of those two or both. 20.6 RL circuits, any of those odds 43 to 47, and energy stored in magnetic fields, any of those odds 49, either 49 or 51 or both. Then additional problems which sort of combine and go across several of those areas, any of those odds 53 through 67 you could do. Take a look at it. All right. Now, since I have a moment here to pause, I'm going to look up and see what I've got as far as, like I said, I know I have that lab ready.
Did you pass out any tests Thursday or Tuesday or today? Sorry.
Wednesday or today?
Yeah, Wednesday.
Okay.
I wasn't here Wednesday.
Right. We had a lab and a test, I think. Let me back up and see. No, wait. I'm thinking my other class. I think I did pass out a test. I'm not sure if I believe I did.
Because the last test I got, I still haven't turned it in yet, was
Which one was it? Oh, I'm in 201. I want to do that.
test
Right. Okay. Okay, you were here for the magnetism lab, weren't you? When we turned off lights and on lights? And,
Yeah.
Yeah, okay. And that was followed by test 6. And
Does
then,
test 6 say test 7 on it?
I don't remember what it says.
Was it
It
the
probably is
photon
off.
one?
Huh?
Was it the photon one?
Okay, that's, yeah. It says a proton is released in such an initial speed. Is that it?
That's not the first question.
Okay, let me see. No. Okay. Oh, okay. My part. That was.
That's the one you gave me last week.
What's that?
That's the one you gave me last week.
Okay. Let me see. Okay. Close. Close the doors. According to the photon energy formula, right? Is that one you just had? Okay. That was the chapter 22 test. Okay. Now I have ready and we did the lab. Did you do that lab? The ray optics?
Because I came on Monday and got that test,
Okay.
but I think you did the lab Wednesday.
Okay. Here is the lab. I do have a copy of it. It says lab 2, but it's really lab 8, I think, or something around there. Okay. Now, yeah, that we did. Whatever day it was, Wednesday. Okay. Now, okay. I feel like I'm covering material more quickly than I'm able to do the tests and stuff. So let's go back and let me if you want a copy of the lab, it says lab 6, but it's not lab 6. Here are some questions to answer, and you can get these from your text. Okay? So there's that.
Is this the next lab we're doing?
Well, actually, it's just a paper lab.
Okay.
So what I would suggest is why don't you start working on it tonight? And this is talking about RC kind of test. I want RL. So why is this here where it is? But we already did RC, I thought. I thought I had RL. Oh, wait. There it is. Okay, that doesn't seem to be the right route. All right, that doesn't seem to be working well. Let's see what we next. Okay. Here's what we're going to do. That's going to be half a lap. We're going to continue with topic 21, start that next time. Okay? So that's going to be half a lap, so just hang on to that until we finish topic 21, and then I'll give you the second half of the lap. Again, it's a paper lab. And that way, those two together will form one lab. They say they're two separate ones, but I don't have time to make up, because either one of them are enough questions for 25 points, but together there'll be more than enough for 25 points. Okay. So, okay, there's that. Now, what we will do is have one test on each chapter though. So I'm going to give you that tonight. But I need it on what I'm missing. This might be it right here. Ah, that is it, right there. Here is a test on topic 20. Okay. Now, I've still got to make out the one for the lenses and mirrors. I've got it made out, I just don't have it formatted for a test yet. So what I would suggest is, why don't you be, oh, that's my original. Sorry about that. Let me get that back. What does that say on it?
I'll take this.
All right. That's my original. I thought I had my original here. Okay. Let's see. uniform.
Take it.
I may not have it yet. See, I thought that was my original, and got two originals. And, there's a copy.
There's nothing on that.
So, why don't you're welcome to work on the lab, or take it home and work on either one. But I'll be here, but what I'm going to do is I've got to go get my flash drive, and I'm going to work on doctoring the test. I have it done, but I just don't have, this is a topic 23 test. I don't have it formatted, so I just got to go through and put lines for you, put that kind of stuff. You see the test bank only has multiple choice questions. I like to see working, so I change them to problems. So I'm going to do that, but I need to go get my flash drive. So you're welcome to work on that. Do you think you'll have any questions? I'll need to leave the system up or start downloading. Okay.